Hey QED Coders, this is Michael. I want to go back through the conversation that I had with Jan and understand Nawiis a little bit better. And then during this process, I'll actually design a historical model in order to support Nawiis. So this should be a pretty good overview of how I think about historical modeling and how I apply it to new applications. So I'm going to go back through this episode right here.
The inspector is allowed to accept that as terminated. But he could also go on. So the number of states changes according to what he does.
All right, so far Jan is talking about this application as a state machine, which makes perfect sense. That's how we built it in the first place. When we are working with historical modeling, however, we don't think about things as state machines anymore. There's one big problem with state machines, and that is that state is local. State evolves at a location. So in a particular machine, you can evolve from one state to the next, and that evolution of state depends upon the messages that it receives and the actions that the user performs at that machine. And so that machine then would send messages to another machine, and that other machine would evolve its state machine. Computer would evolve its state machine. Now, the problem is, in a distributed system, it's not just two machines, and it's not just messages flowing in one direction. Messages are flowing in all directions all the time. And so the order in which messages arrive at one computer will be different than the order in which they arrive at another computer. And if we're just thinking about state machines, then the order in which you take those transitions matters a lot. So instead, historical modeling takes on a different foundation, not state transitions, but instead a foundation that does not depend upon order. It's a mathematical foundation that is by its very nature commutative, and that's directed acyclic graphs. I'm going to try to understand the application from the perspective of the state machine, but then translate it into a historical model and build a directed acyclic graph. So let's keep watching.
But so instead of having every field being a state, I could say my state is I'm going up to the first ballast. Next state, going down. Next state, going up after the first ballast, going down after the first ballast. And then within that state, I could still have substates, but these substates, they are variable.
Okay, so overall, we are measuring, and there's a certain order in which the person taking the measurements is supposed to perform this operation. So they're supposed to increase up to the ballast, but not including the ballast, and then decrease back down to zero, drive the ballast onto the scale, increase, and then decrease back to ballast weight. And there's that particular order, and so as Jan is describing it here, you can think of the measurement as being that state machine. So it transitions through all those different states as they take the measurements. Here he's talking about variability within the substates. So before you actually take a measurement, you have to perform these different actions, and then you get through this little state machine, and now you can perform the next measurement. Let's try to understand those substates, and then we'll come back and we'll try to draw some pictures, see what's going on.
So now he reads 10,000, and then you're going to add small weights, 2 kilo each time.
Until you see the
and at a certain
number change.
Time, at a certain moment, it will go to 10,020.
Okay. And so that's how the error was 14 instead of the full 20.
Yeah, because you really have the point where he switches to the next level.
Yeah.
And that allows you to calculate the real error.
Yeah.
But so all these steps could be substates, and also even in the user interface. So one line could be a view model.
Okay, so each one of those steps is a substate within a smaller state machine. And then he makes this observation here, which took me a long time to understand what he was talking about here, that these substates are represented in the user interface directly. We're going to get into this in a bit more detail, but usually in a user interface, the navigation, moving from field to field, is just transient. You could think of that as a state machine if you wanted to in a regular user interface, but most of the time it's just which field has focus, and you just go from this one to this one to this one. Maybe tab traverses a state machine, but you usually don't model it that way because the user just gets to move around. None of that's persisted. However, what he's talking about here is the fact that the field that is currently has focus is actually a representation of the state of the system, that it is truly part of the persistent state. And that's going to be really important when we get to modeling this in Janaga. So let's dive into that in a little bit more detail here.
So that's the weight scale up to 60,000 kilo. And I told the system that I only have for 30,000 kilo certified weights with me. Mm-hmm. So the system tells me you have to put 40 kilo, you have to put 400 kilo, 10,000 kilo, and 30,000 kilo.
Okay, so we're starting to get into the meat of the process here. You tell the system what weights you have with you, and then the system tells you what measurements you need to make. So that's probably bound up into some regulations. That is a policy. So there's some policy, which is encoded as an algorithm that takes that input of how, what weights do I have, and then gives you back that particular list. That is going to be very important as well. So in fact, let me start by capturing some of that. Another word for input and output, you could call these independent variables and these dependent variables. So independent variables are the things that the user themselves can change. Dependent variables are computed based on some kind of algorithm. So in this case, this algorithm is encoding a policy.
I can still change it. If I say I don't want to put 400, but I want to put, I'm not allowed to change this one.
That was important right there. He's not allowed to change those variables. Those are dependent variables. You can't change them.
What do you measure? Yeah, you put 40 kilo. I measure, for example, it gives me 60 kilo on the indicator.
Yeah, instant fail.
Yeah. And then to go to 80 kilo, I put 2 kilo, 4 kilo, 6 kilo. For example, I have to add 8 kilo. Then you say, okay, so your real error is 22 kilo, fail.
Okay, so we've got some more dependent and independent variables on this one line. We show the indicator, what the indicator says, and then we show this delta L. How many additional kilograms do I have to add before I get to the next indicator step? Then it does more calculations and it calculates some dependent variables. So let me capture that. All right, so this appears to be the calculation that's happening. We've got our actual measurement, our indicator reading, and our delta L. So these are the numbers that the user enters here and here. And then it calculates this error E and this error EC. And so we've got those two coming out of this calculation. So far, this is the flow of information if we think about dependent and independent variables. The user enters this, and we've calculated these things. All right, well, let's see a bit more.
I can add more, but I don't do that. I do tab.
And then it sorts. Interesting. Okay. It
sorts, yeah. But that means that my decisions are going to influence the whole workflow.
Yeah, that's very important. So the user's decisions influences the workflow. The user just made some decisions about which additional measurements to take, and they entered those in. So yeah, this is really where I started thinking about, how do we combine these dependent and independent measurement numbers? Coming back here, we've got our official measurements, and these are dependent. We calculated them based on the weights that were available. But then the user enters some additional unofficial measurements. I don't know if that's the proper word to use there, but let's go ahead and capture that down here. And those are independent because the user gets to enter them. They are not calculated, so they're not dependent. So we've got our unofficial measurements. In fact, let me scoot these up here. Okay, so we've got our official measurements and our unofficial measurements, and so we are going to combine those two into the set of measurements that we actually see. Typically, the independent variables are captured as historical facts. Somebody made that decision, and so we record that decision. The dependent variables we don't record as facts because we already have the facts and the policy or algorithm that helped us to determine that dependent variable. We don't need to store those dependent variables as facts. And in fact, not storing them as facts really helps with the system being able to converge. That I don't calculate some dependent variables based on an incomplete set of independent variables, an incomplete set of facts, and then record that, and then I have to later come back and say, oh wait, I learned something new, that's no longer right, and have to change that. If I don't record it in the first place, then there's no problem with the system getting out of sync and having to get back into sync. So that's usually the way that I like to do it. I suspect that in this application, that might need to change. But I'm not going to jump there right away. I really want to justify that. I want to prove that's necessary. So this is the path that I'm seeing. So we enter our weights available and then determine the measurements to make. We've got our official measurements. The user can enter unofficial measurements, and then you union and sort those two lists in order to get to the list of measurements. And now for each of those, you take that measurement and then a couple of independent variables that the user is able to enter on that same line, the indicator reading, delta L, calculate the error, and you show the E and EC for that particular line. So I think this is getting to the core of the system, how information flows.
I can add more, but I don't do that. I do tab.
And then it sorts. Interesting. Okay.
Sorts, yeah. But that means that my decisions are going to influence the whole workflow.
Yeah, so I think we've got two different tiers of facts. There are the measurements. So you've come here to take these measurements. Those are the facts that you're ultimately after. But then there's this intermediate tier, which is how you've set up the experiment. So yeah, the different weights that you've added, that's another. So the two tiers that I'm talking about are analogous to these two sets of independent variables. I get to say what my unofficial measurements will be that I'm going to union and sort into the official ones. And then I also actually take those readings and I capture those as facts. So basically any persistent independent variable is going to be recorded as a fact. We're going to have something in the historical model that represents it. So these are the two tiers. But let's go ahead and draw those as historical facts. Okay, so these are the words that I've come up with, and they're probably not the right words, so this is the danger of doing this sort of thing without a domain expert sitting right there. The words that I came up with was an inspection. That's this whole process, and so the inspection is where I capture the independent variables out here, the weights that are available. Then measurement is the word that I came up with for the measurements that I'm going to take. So these are the unofficial measurements that I add to the inspection. And then a reading is what I came up with for what does the indicator say, and how much delta L did I need to add to get to the next indicator reading. So I capture that information in the reading. So to make that a little bit clearer, what I'll do is I will write a specific scenario where I've got the inspection, measurement, and reading facts that show exactly what Jan is doing right now.
60 kilo on
wow.
the indicator.
Yeah, instant fail.
Yeah. And then to go to 80 kilo, I put 2 kilo, 4 kilo, 6 kilo. For example, I have to add 8 kilo. Then you say, okay, so your real error is 22 kilo, fail.
Okay, so in this scenario, let's see what I came up with. So we've got the weights available, 30,000. And from there, it calculated some official measurements. And then I added the unofficial measurements with the target weight of 2,000, 5,000, and 20,000. And so this is just capturing the independent variables, which is what I typically like to do. Only the independent variables are captured as facts. But then we run into this problem. You saw an indicator of 60 kilos and then a delta L of 8. And so I've got this reading, this indicator reading of 60 and the delta L of 8. Which one do I attach it to? It's not one of these. It's one of the unofficial measurements. It needs to have a predecessor of some sort. Which one do I... so does that mean that I actually need predecessor? I need facts for these unofficial, or for these official measurements, these dependent. So that seems to indicate that I need facts for these dependent variables, these official measurements. I'm going to try that out, and I'll see if that's the way that I want to go. Let me go ahead and model that fully. Okay, so here is one possible way that we can model this, where we've got an inspection, and we've got several different measurements, but now we have an is-official property of those measurements. 40 and 400 were official. They were dependent on the weights available. The 2,000 and 5,000 are not official. The inspector added those.
Now I can change it here. I can make 2,500. I can even make, for example, here, let's say 7,000.
Yeah.
I go back.
And
now you have the 7,000 before the 5,000.
Yeah.
You'll sort it.
Okay.
Yeah.
But you're okay. So this is saying that you can change an unofficial measure. So you're able to go in there and edit that. Because you had to shift tab, I think that was an important UI indication there. If you had some indications, some, what did I call them, readings. Let me double check readings. If you had readings, then shift tabbing would destroy that information, I think. And so you're going back, basically back in time and making a change and then going forward again. So I think the way that would show up in these facts is that when you went back in time, you're not changing this one, you are creating a brand new one. So here would be a brand new one that you typed in 7,000. And just finish that off. Yep, that's pointing up there. So that brand new measurement is now part of this set, but this one is no longer part of that set. And so therefore you need to implement the good old delete pattern. So we can have a measurement delete with a timestamp deleted at any particular time and say, I actually deleted that measurement. Okay. And now from here we can get back to the question about these state machines, the outer states and the inner states. How does that translate to a historical model? And so this is the way that I see that working. We've got our facts. We run a projection. This projection given an inspection, project measurements and readings. So now that turns that into a structure. You can think of this as a JSON object. This is your typical parent-child kind of a relationship. And so we've got an inspection projection and multiple measurement projections. And so then for each one of these, I'm capturing the reading up. One thing that I did not capture in here is that we've got readings up and reading down. So this is actually a different fact than a down reading would be. But so yeah, you can see that this projection has already taken into account the delete pattern. So the 2000 no longer appears in here, just the 7000. So it does that projection, gets us this data structure, and then we can run it through some additional computations. One of those computations will be to compute the next action. Given this structure, can you kind of eyeball that and see what the next action should be? The next action should be to collect the reading up on this measurement here. And so that means that I will have the next action of the focus should be on the up indicator reading. Adding a fact causes the projection to change, which causes the dependent state to change. And so now you're doing that without state machines. What if we shift tab and we go back? Then we capture a reading up delete. And we say deleted at now, some date that we capture right there. And so doing that will cause this to run. That will no longer be there, so this will go away. And so we'll be right back to line 1. So shift tab creates a fact, recomputes projection, recomputes dependent state. All without state machines. You get the idea. This compute next action, what it does is it looks at the list of measurements, finds the first measurement that does not have a reading up. If all of them have a reading up, then it finds the last measurement that does not have a reading down, because we need to traverse this from the other direction. And then it says, that's what should have focus. So that is the way that I would like to structure this system. Not a state machine, but set of facts, projection, and some dependent state. And this is what the view model should look like. The view model starts with this specification, does all this computation, and ends with some properties that that show you what the user interface should be doing. And you know what? You know what does this kind of compute next action and update some dependent properties? That's Assisticant. Hey, maybe this is a great time to bring Assisticant back into the fold. And so yeah, next time we will build this view model using Assisticant and Janaga, and we will make all of this interaction work. So come on back for that.